Okay, good afternoon, everyone. I want to welcome you to another new month. Oh, sorry, another new week. And of course, also to welcome you to Apply Regression Analysis class. Today we're starting chapter 4. Uh, of course, that was centered on interpretation of May effects. You know, um, if we're seeking to characterize relationship among variables, after we've specified our model, we've done parameter estimation. I think the next on the line after we have performed what I call diagnostic testing is to start interpreting. So interpretation become very, very necessary because without providing an interpretation, of course, there's possibility that stakeholder may not benefit from your efforts. So today I present to you interpretation of main effects. We're actually going to be focusing on main effects today. Of course, in another lecture, where it's going to be interaction effects. So today I'm going to walk you through main effect, what we mean by main effect. Okay, so in the outline, I'm going to talk about main effects. I'm also going to talk about situation where in your regression model, you have the combination of, maybe you have more than one predator. One is categorical and the other one is quantitative. So how do we interpret that kind of model? Then how do we also interpret a logarithmic mean function? Now, when I talk about logarithmic mean function, probably uh, maybe the response variable is on logarithmic scale. Okay, how do we interpret stuff like that? What of in a situation whereby uh, one of the independent variable is on logarithmic scale? In fact, at times we can see situation where both the response and the predator, they are going to be on logarithmic scale. So how do we interpret? Okay, I'm actually going to walk you through that. But let me first say this. If I'm talking about main effects, I want to start with main effects. Okay, when we talk about main effects, I actually want to figure out the direct effect of a particular predator, okay, on the response after adjusting for other predators in the model. I'm going to say this again. When I talk about main effects, I'm actually trying to figure out the direct effect of a particular predator on the response, keeping other predators at constant. So that is exactly uh, what I mean by main effect. Okay, so I'm actually going to go take a look at this. If you look at the first model, one second. I think I'm going to use my pointer now. Okay, so is that working? Okay, now if you take a look at this model, of course, what is saying here is a mean function for simple linear regression. So here I'm talking about the expected value of y or given s. This is a conditional mean. Okay, this is a mean function. I'm only going to be focusing and focusing on x1. The x1 is the predator here. But when you take a look at 3.1, a new variable has been added, which we call S2. And let me tell you, the mean function become extended. Okay, this is an extended mean function. But why are we adding S2? Okay, we're actually adding the variable S2, maybe because the X1 may not be able to explain all the variations, in the response. And that was why I said, you know, there's possibility, adding x2 is to explain, parts of y that has not been explained by x1. Let me tell you this. X1 is only going to explain part of y, part of the response. Okay. Well, maybe there's probably some part of the response that cannot be explained by X1, and we believe adding X2, of course, that will do the job. We don't just add a variable to a model. Okay. There's a reason. So what I'm going to walk you through, how can we actually, um, you know, investigate the significance of the variable that I'm adding into a model. But you know what? I'm going to start using United Nations on data. Okay. If you want to get this in now, of course, I uploaded. You can now have access to the R materials, that you're using in this class. I think I uploaded that last week. You can check. It contains all the the TA is going to be extracting whatever is going to walk you through, from that very material. And of course, I also added another material that contain data in R. Okay, the UN11 is one of the data set, that you can have access to. So I'm using United Nations data set, in the data structure. We got life expectancy. This guy is a life expectancy. And of course, this guy is the logarithm of maybe per capita GDP. And of course, we had another variable called fertility. Okay. But let me first say this. Okay. If you pay attention to this guy, you're actually going to see that that guy is on logarithmic scale. Okay. So, but why the life expectancy and the fertility, they are not on the logarithmic scale. So whenever you want to interpret a model that contain, where one of the variable is on logarithmic scale, you need to be very cautious when you are interpreting. I'm going to walk you through all of that. Okay, now this is what we want to talk about. This guy is a response, life expectancy. Of course, every country want to have improvement on the life expectancy. And of course, uh, we got some factors, that have connection to life expectancy, okay, like the per capita GDP and the fertility. Now, talk about fertility here. We're talking about the average number of children per women, okay? But I wanted to take a look at the scatter plots. Of course, if I'm seeking relationship between variables, and of course, I want to have a sense of what I'm going to be specifying, whether it's going to be a straight line or a quadratic or whatever I need to first get a scatter plot. I needed to take a look at this guy. Okay, this is a scatter plot between the life expectancy and the logarithm of the per capita GDP. Okay, why do you think I did not use the one that has to do with just per capita GDP without the logarithm scale? I want to award an extra credit. I don't joke with my extra credit. Okay, I don't joke with my extra credit. I want to award an extra credit now. Why is it that I actually choose logarithm of per capita GDP? Okay, here, why not just the per capita GDP without logarithm? Can somebody tell me why? For extra credits. Because if you take a look at the per capita GDP, of course, that is on the logarithm scale. If I remove the logarithm, okay, why not removing the logarithm and just plot? Yep, go ahead. Exactly. So which means uh and before we can actually use a linear, we call it linear regression, we expect a linear relationship. So with the one without a logarithmic scale, the relationship is not going to be a straight line. So send me a message for extra credit. Good job. So and that is why we take the log. We don't just do what we do. We got a reason why we do what we do. But when you take a look at the one at the other hand, okay, when you look at this at the other hand, of course, uh, that is a life expectancy against fertility. So now, when you take a look at these two are giving me information. The first one is trying to tell me it's like I have a positive relationship, and the second one is trying to tell me the relationship is negative. Okay, so the scatter plots become necessary as part of the preliminary investigation if I want to have a sense of the relationship between the variables. But you know what I want to do? I want to differentiate, between what we call a marginal plots and the variable added plots. But before going there, let's take a look at the marginal plots. Take a look at this. When I say marginal, When I say marginal, even though I know that there are two variables here that have relationship with the response variable based on the scatter plot that I generated. If you take a look at the scatter plot that I generated, it actually shows that there's a linear relationship between the life expectancy and the log of per capita GDP, and there's also a linear relationship between the life expectancy and fertility. So based on this scatter plot, I'm having a kind of idea that, of course, I need to consider two explanatory variables. But what if in a situation where I decided to ignore one? If you take a look at 3.2, okay, if you take a look at this guy now, okay, if you take a look at this guy, okay, I'm actually ignoring fertility. A variable called fertility is ignored totally here because this is an estimated mean function for life expectancy and the logarithm of per capita GDP. Okay, now here I'm actually ignoring the life expectancy. Okay, now the plot that will be based on this is called marginal plot. So which means the scatter plot here, each of that is called marginal plots. Okay, they are marginal. When I say marginal, even though there are two variables that can explain why, I'm only focusing on one of them, ignoring the other. That's what we call marginal plots. Does that make sense? Okay. Now, and the mean equation for that marginal plot, for one of the marginal plot is what I'm showcasing right now. Okay. Now, every mean equation is actually going to come with the R squared. Okay. So the R squared here is about 60%. So what we're trying to say here is that the variable of interest, okay, the variable of interest actually explain, which is the logarithm of per capita GDP, was able to explain 60% variation out of 100% variation in the response variable, the life expectancy. Okay, so here I actually ignored one of the variable. Okay, so this is the other mean function. Okay, when you take a look at this guy now, okay, the mean function here is when I try to ignore the logarithm of per capita GDP, I'm only looking at the effect of fertility on the life expectancy. And of course, when you look at the slope is negative, okay? And how do we interpret that? Okay, so if I want to interpret this, okay, I'm actually going to say for every unit increase in fertility, and when I say every unit increase in fertility, I'm trying to what is fertility in this case? It's like the number of children, a woman, let me show you. I think I actually defined that the other time. right here. Take a look at this. That is the fertility here is defined as the average number of children per woman. Okay, the average number of children per woman. Okay, now if that go up by one, if a woman has one more, okay, one more child, okay, this guy is trying to say on average, okay, on average, okay, what is going to happen is that we expect the life expectancy to decrease by 6.224. Why decrease? Because of a negative, okay? And if I really want to know out of the 100% variation in the life expectancy, okay, how much of that is the fertility able to explain? Okay, the fertility here, because of the R square that we have, okay, uh, the R square is 0.678. Of course, that explains 68% of the variability in the life expectancy. We're talking about this explanation. Don't forget, we believe there's 100% variation in the response. I'm trying to figure out how many of that, the variable of interest, is able to explain. But let me tell you this. This is also a marginal plot because we are ignoring another potential variable. The potential variable that has a connection to life expectancy is the logarithm of the per capita GDP. Okay, so that is marginal plots. Okay, once again, when I say marginal plot, okay, the marginal plots are actually talking about, you trying to look at the effects of a particular explanatory variable on the response, ignoring another potential variable that could have a connection to the response. Is there any question here before moving forward? Any question? Okay, now I'm moving. I'm actually going to move right now. And I want to talk about the added variable plots. Okay. Now, in the added variable plots, instead of me to ignore, I totally ignore a particular variable. Okay. I also want to add the variable, but I don't just want to add this variable. I only want to add variable that makes sense. Okay. I was telling my wife one time, I said, no, my wife was asking me that you don't have friends. I said, oh, okay. Everybody is my friend, but those one that I move closer, I think I actually favor quality to quantity. Quality to quantity. I prefer quality. Okay. I have a friend that's going to have effects on me. I'm also going to have a positive effect on that. So what I'm going to say here is we don't just want to add in the name of adding variables, not just for adding sake. We really want to add a variable that will make sense. But how are we going to know? So I want to talk about the added variable plots. Okay. Now, in the added variable plots, I needed to pay attention. If I really want to know if I've added x1 and I want to add another variable x2, okay, I really want to justify the inclusion of x2 into my model. This is what I'm actually going to do. Take a look at this. The first one here, the first one here. Okay, I need to, I'm for first looking into relationship between the life expectancy and the logarithm of PPGDP, okay, with the mean function that we derived the other time. Okay, let's calculate residual, okay, which means what I'm trying to do is, then before first look at relationship between Y and X1, then I get a residual. I know residual will exist. Residual will exist because I do not expect X1 to explain all the variation in Y. Okay, I'm going to keep that residual that I compute from that scenario. Now, I'm now going to go into another scenario right now. In this second scenario, okay, what I'm going to do is to regress the new variable x2, okay, and I'm actually going to regress that on x1. Okay, that's what you see here. Fertility, which is a new variable. I'm actually going to regress that on the previous predator that I've considered. Then from there, I'm also going to compute the residual. I got two forms of residual now. The first residual is actually going to be, some part of why the old variable x1 was not able to explain. The second residual is actually going to be the part of the new residual, the part of the new the new response. If you take a look at that very S2 is a predator, but I want to use it as a response. So what I'm actually going to say here based on this is I'm getting residual based on this, and that is the part of the new predator the old predator was unable to explain. Okay, and when I do that, if I now want to get my added variable plot, then what I'm going to do is to now plot the first against the second, and I'm going to show you plotting the first against the second, and plotting residual against residual from the first one, where when I regress y on s1, and the second one when I regress s2 on x1. And you're going to see what I'm going to have. Okay, take a look at this. This guy, you see error cap, error cap. That is the residual from the first scenario. I'm plotting that against the residual from the second scenario. This is what we call variable added plots. But can we do something now? If you take a look at what I have, if you take a look at this guy, okay, if you take a look at this guy, you see life, I wrote residual from life expectancy on the log of PPGDP against the residual from fertility on the log or PPGDP. But when you take a look at the second one here, okay, the second one here is a marginal plot. Okay, oh my God, the second one is a marginal plot, where I have the life expectancy on fertility. That one is also talking about fertility, but when you take a look at it too, there's variation in this compared to that. There is more variation in the marginal plots compared to the variable added plots. If you take a look at the variable added plot, okay, I can see, most majority of the point cluster around, particularly when you take a look at here. Can you see that? But here, can you see that variations? Okay, and that is to tell you, okay, the new variable that we're adding, okay, is also the presence of it in the model, okay, is actually going to explain some variations in the response. Okay, now can we have a model from that? Okay, I'm actually going to show you now because in the two, there's going to be slope. The slope for this guy, the slope for that. Take a look at this. Okay, when I ignore the log PPG, the log per capita GDP, you see what I have. When I adjust for that in the marginal plot, okay, we actually ignore something, but in the our variable added plot, we adjust for it. We didn't ignore it. We adjust for that, and you can see that the slope are not the same. Okay, from what I'm seeing, okay, I said the slope in the added variable plot is about 30% smaller than the slope in the plot that ignore that. And I say, although in this instance, after adjusting for that, the effect of fertility is still important. Okay, and of course, further, if I'm going to give you a further detail on how we can take a position statistically, conducting a standard statistical test, to be able to justify adding a variable into a model. We don't just add a variable into a model. Okay. Okay. Now I'm going to go into this away from that. I want to consider a situation where, because we also need to consider the nature of the explanatory variable. The interpretation you give depends on the nature of the explanatory variables. Now, let's say I want to consider a situation where I have one of the predator variable is categorical and the other one is quantitative. How do we interpret that? But let's first start from here. I want to consider this. I want to explore relationship between wage and marital status. Marital status is categorical because it has levels, married or single. And of course, you know, if you take a look at this, I call X status and I call the Y is wage. Okay, what I'm just showing you here is when I'm just looking at a simple linear regression where I'm really looking at the effects of status, on the wage. This is similar to what you did in a lower level statistics where you are comparing two groups. You're comparing two groups, and the groups here is going to be you're comparing the salaries, the wages of married and single workers where you do two sample t-tests. This is similar to that. So this is simple linear regression. Now, there's something I want you to see. Okay, this is the plot. Okay, you're going to see 0, 1 because one of the predator variable, the predator variable is categorical, it has levels. So we have to use a label 0, 1. Okay, now 0, 1 is going to 0, 1 for married and 1 for single. Okay, I can decide to go other way. But let me tell you this. When I run it in R, okay, if I have this result, there's something I need you to see. Pay attention. In my output is showing single. At times, Arrow can automatically decide whatever that is showing in your output, that is what Arrow coded as 1. It means Arrow has coded single as 1, married as 0. So whatever that show up, we got two levels of that, and you can see single, then it has coded that as 1. Now, if you take a look at this now, this is using the estimate here. This is the feeder model. Now, how do we interpret this? This is a mean estimated mean function when this is like a marginal, going to get a marginal plot from here. We are totally ignoring other potential factors that could have effect on wage. We're only talking about marital status. So if I want to interpret that, I'm actually going to say, based on the model, single workers earn 109 cents, because that's $1.09. 109 cents less per hour than the married workers on average. That is the interpretation of this model. But let me tell you this. We're going to argue this out because we want to believe there are some potential variables that have connection to wage that are missing in this model. Let us start. What if we now incorporate that? Now take a look at this. Now I want to add, in addition to status, I actually want to add the years of experience. The years of experience of workers also play a very huge role in determining the wage. Now, when you take a look at this, the nature of these variables become very important. Okay, the years of experience is continuous. Okay, but the status is categorical. So this is a combination of a categorical predator and a continuous predator. I wanted to take a look at that. Now, when we run the regression, this is what we got. And let's take a look at the estimated regression model. This is the estimated regression model. And let me tell you this. Our main variable of interest is marital status. But we believe that there's a potential variable that's also having effect. So what we're doing right now is like we are incorporating the experience. The experience was not the primary focus of interest. So, but when we incorporate experience into the model, let's see how the interpretation of the status is going to change. Take a look at this now. Initially, it was 109 cents. Okay, that the single workers actually had less, per hour than the married workers. But when the years of experience is incorporated, that's a 90 cents. That's a gain in cents by single workers after incorporating experience. Okay, now do you know with this model, with what I have right now, I can create two set of models. Pay attention. I can create two set of models. I can create a model for married workers. I can create a model for single workers. Now, if I want to create a model for a single worker, I'm actually going to plug in single. I'm going to plug in one. Wherever I see single, I'm actually going to plug in one. Okay, when I plug in one, okay, my intercept is going to change because I'm going to have 8.86 minus 0.90, but the slope remain the same. The slope for experience is going to be 0.027. Okay, but you know what? What if if I want to obtain for the married workers, I'm actually going to plug in zero here. When I plug in zero, okay, this is going to be the new model. Does that make sense? So from the general model, we can actually, make statistical inference for married workers and for single workers. Okay, now the next that I'm going to talk about, okay, after all of that, you can now answer this question. You say, okay, when the experience is 20, how much less does a single worker earn than a married worker on average? Of course, you're actually going to use the model for single worker. Then this one, you're going to use the model, the one for married, for married worker. And of course, when it has the general question, okay, they can ask the general question about the status. When I know the status of the worker, and at the same time, I know the years of experience, of course, I should be ready. I'm actually going to use the general model here. Okay, that's what I'm going to use. Okay, I want you to to pay attention to that. Okay, now, how are we going to do the interpretation? Please pay attention to this. I said, when we control for experience, because incorporating experience into the model, it means we're not ignoring that. We're actually adjusting for that. We're keeping that constant. Okay, then we're going to say, focusing on this now. Okay, we're going to say, okay, then we can now interpret that after we have already adjusted for experience. And this is what I'm trying to say here, that I said when we control for experience, that is, we hold that as constant, a single worker earns 90 cents less than a married worker on average. Take a look at that. That's after controlling for experience. Now, we can also argue it out. Okay, when we continue to dig further, there could be other potential factors, that we also need to incorporate in terms of covariate, that may have a connection to the wage. Okay, now because of that, in addition to experience, we want to consider years of education and sector a worker belong. Okay, because we believe the sector the worker belong may also have a potential connection to the wage. And not only that, the years of experience or the years of education. But if you take a look at what I have right now, oh my God, I got a lot of explanatory variable, the years of experience, the years of education, the sector the worker belong, and the marital status. I got four. But when you take a look into these four, the years of experience, the years of education, they are continuous. I'm going to say that again. The continuous mean they do not have levels, no categories. But when you take a look at sector has categories. Status also has categories. Now, when you take a look at the sectors, these are the sectors that we have. They can be clerical and so on like that. But you know what's going to happen? If you put the data in R, Arrow will automatically remove one and make it a reference. Let's see. Okay, take a look at this. This is the result. And I need you to pay attention. Okay, I have years of experience. It's only going to be reported once. Years of education, because those are continuous. But when you take a look at the sector is categorical. Okay, uh, you know, there is a particular sector missing out. Can somebody check? A particular sector is missing out. What is that? Look at the yellow. There's a particular sector. Arrow has referenced that category. What is that? Let me take you back. Clerical. Okay, take a look at this. Notice a clerical here. How do we automatically reference one? When you have a categorical, when you have a variable that's categorical with two levels, so if you have 8 levels, I will only report 7. If it is 2, I will report 1. Okay, now the other one is being referenced. So take a look at this. Okay, here status single. Okay, they are two, married and single. Arrow is reporting single. It means it reference married is in the intercept. Now in the sector, also reference clerical in the intercept. Now, right now, let us now go back to the primary of interest, the variable of interest. Okay, we're coming back here for single. That has drastically reduced. We started from 109 cents all the way to 90 cents. Right now, when all other variables or important variables are included, what happened now? That's about 40 cents. Can you see that? That's about 40 cents. Now, if I now want to take you to the general interpretation now, when I first started, take a look at the first one. When I first started, when I only focus on marital status only, okay, I said when not controlling for any other labor force factor, okay, single worker make 109 cents less per hour than the married workers on average. When I added experience, okay, that go up to 90 cents. I mean, the guy go up to 90 cents, which means what they are losing go down to 90 cents. Okay, when I incorporated the years of education, okay, and the sector, okay, particular worker belong, that go to 40 cents. Take a look at that. So that is going to tell you when an important variable is missing in your model, okay, you can't trust your regression coefficient. Initially, it making us to believe it's 109 cents that the married, that the single worker actually earn less than the married on average. When we incorporate that another important variable, it go to 90 cents. And right now, we're on 40 cents. Okay. And if I go back, if you want to write the model, take a look at this. Uh, this is going to be the model. Okay. I just leave you to write what is missing. Of course, what is missing, the intercept, you're going to write that guy there. Okay. The one for experience, you're going to put that guy here. Okay. And the one for education, that is what is missing. You're going to put that guy here. Okay. And the one for status single, okay, is this guy. Okay. You're going to put that here. So that's it. You're actually going to have an extended mean equation. Okay. Now I'm going to move now. Now, please pay attention. I was trying the research question initially focused on this. The research question initially actually focused on the relationship between wage and marital status. Okay, but you know what? Situation where some important variables that also have connection to the wage missing in your model. I'm actually going to say that model is misspecified. There are 3 ways you can misspecify a model. Model misspecification is not good. Number 1 is either you misspecify the functional form of a model. Number 2, maybe you include wrong variables in a model. Number 3, maybe key important variables are missing. Okay, now uh, you know, here the response variable was wage, but the status was the main variable of interest. But uh, we now had a covariate. The covariate are the years of experience, the years of education, and the sector worker belongs. Okay, and that was why I said controlling for covariate is especially important when you analyze data from an observation study. We got two types of studies: got observational study and experimental study. In experimental study, of course, the researchers control, manipulate, okay, randomize, but you do not have control on the observational study. You don't have such control. And that is the reason why, uh, you know, when a relationship exists, when association exists, I cannot conclude causation. Association does not imply causation, but there's something you can do that can make association to translate into causation when you adjust for important variables. Okay, now I want to go to the last objective of today that I call interpretation of a logarithmic mean function. Please pay attention. Okay, interpretation of logarithmic mean function. Okay, this when your response variable is a log, that becomes a logarithmic mean function. Okay, I want to use this example that we have here. Okay, here we're trying to use a particular data set. What are the factors that explain Minnesota use of water? And of course, the response variable here is log. Okay, when I use the first model, here I'm only looking into the effect of year, because we believe that as year goes on, there's possibility the use of water increases. That's in model one. In model two, we're considering, in addition to year, we're also considering the municipal precipitation. Okay, and of course, when you take a look at the model three, we actually considering a lot of factors. Okay, but there's something I need you to pay attention to. Look at the year and look at the log of the population. Okay, we expect population to be significant. When you take a look at this, asterisk, do you see asterisk on that, right? Asterisk indicates significance. So the model 3 is only telling me here that what is significant is precipitation to the use of water. But we all know population also is significant. But here, it's not significant. And the reason why it's not significant, because the year and the municipal population, they're giving the same statistical information. They are correlating. Okay. When two variables in a model, okay, are correlating, okay, it could be problematic to the model. Of course, in one of the classes, we're going to discuss multicollinearity. It's a problem. Okay. But I'm not going there. Okay. I'm only trying to show you right now, where the response variable is log, and one of the predator is also log. Okay, how can we interpret? But uh, the essence of of logarithm, okay, I'm going to tell you in another example where I'm considering effects of mice on fuel. For the mice, okay, and initially when you take a look at this, when we plot fuel consumption against mice, that was not linear. And when you take the log, you can see here, you're taking the log, and that bring out the linear relationship. So we don't just do the log, we don't just put a logarithm on a variable. Okay, it's a way of transformation. Okay, making sure we want to attain linearity. Okay, so if I have that, take a look at this guy. This is a logarithmic mean function. Y is log, but none of the predator is actually log. How do we make the interpretation? Okay, I actually do some, you know, proof here, but I'm going to take you to the final. Take a look at this. Okay, whenever the response is on a logarithmic scale, okay, and you want to, and maybe one of the, maybe the predictor variable of interest is not log. The interpretation is going to be for a unit increase in X. Okay. So when you talk about a unit increase in S, you're going to talk about the percentage increase in Y. Does that make sense? Now, for instance, and this is what we're going to be using. Take a look at this. It means before you can interpret the beta that you got in the model, you need to first plug it here. When you plug it here, for example, if my beta 1 is 0.3, for instance, and that very 0.3 correspond to an explanatory variable that is not logged, but the response variable is logged. I'm going to put 0.3 into the mode, into this one, and that give me 34%. So what I'm going to say, a unit increase in X bring about 34% increase in Y. Does that make sense? So whenever the response is log and the predator is not log, you're only going to talk about a change in X will bring about a percentage change in S, in Y. Okay. If that's what of in a situation where you got this guy, negative is 0.2. Okay. Now if you plug that in, you're actually gonna get this. Then you're going to talk about percentage decrease because of the negative. Okay, I just wanted to pay attention to that. Now, but I want to come back to the United Nations data. Take a look at this. Look at the estimated mean function. This is a logarithmic mean function, but let me tell you this. The response variable is logged. One of the explanatory variable is log. Please pay attention. Now, if I want to do interpretation, I do interpretation to the explanatory variable one at a time. Okay, if I want to take a look at this. If I want to make an interpretation, let's say between this and this. Okay, a unit increase in the life expectancy, okay, will lead to a percentage change in the fertility. Does that make sense? But and that was why, if the beta, the beta here is negative is 0.028. When I plug that in, then I'm gonna say this. I'm gonna say 2.8 decrease in fertility. But how am I going to interpret this guy? Oh my God, if I want to do this one and I have a log on log, then the two of them will involve percentages. For log of PPGDP, I'm going to say a percentage increase. Okay, 1% increase in the logarithm of per capita GDP, then I'm going to say would lead to a change in the percentage of the log fertility. Does that make sense on the fertility? So that is how we do that. Finally, we've been talking about R squared. Okay, R squared is a notation for coefficient of determination. It tells us how much percentage variation in the response a model can explain. Okay, but before you can use your R square, make sure you're talking about straight line. R square is only appropriate when you are dealing with a straight with a linear or form of a model, a straight line. But so which means A, B, C, D, A, B, C, okay, A, B, and C, of course, R square makes sense. But here, we're talking about R squared. R square is not appropriate in that situation. The first one is a curve. The second one is a possibility of outlier. And the third, and we take a look at this very one, there's also an issue. So make sure I told you the other time, our models are not failing us. Maybe we are the one that we're not doing the right thing. Okay. What am I having next? effect plots. That's what I'm having next. Is there any question before I go today? Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone.